In today's video, here is a nice problem. It's coming from Hungarian Mathematics Olympiad edition 1901. This problem is more than 100 years old. So for all n as a positive integer such that we have this condition for not divides n makes this expression divisible by number 5. Okay, so this is the condition. So the confusion of this problem is this one. Okay, technically understanding the question is a part of answer. Okay, you guys, you can give the hands to this problem prior to solution. Go ahead, pause this video when you come back to see the full solution. Okay, now let's jump into this one. Since we are working on this condition, we are going to display all the cases of this condition and to see where we have divisibility happen. Okay, let's get started with this one. So I'm going to see for not divides n implies I'm going to divide this one into three cases. We have three options. N equals 2 is multiplied by number 1, okay, or n equals 2 is multiplied by a must be odd, or n itself is a odd. Okay, all these cases make for not divides n. Okay, in the other word, for not divides n, which means n it takes only these three possibilities, it cannot take anything else. Okay, so for this one we have a number 1 here, we have 2 as a multiplier. This one is a congruent to 2 mod 4. If I'm going to reduce this one to mod 4, we get number 2 as a reminder. So for this one, so a is a odd, it could be the factorization prime, it could be have 1 or 2 or 3 and so on and so forth of the prime numbers. Okay, for example, if we have a equals 15, which means we have 2 prime numbers here, 3 and 5. If you have this one equals 21, we have 3 and 7 and so on and so forth. Okay, for the last one, n is arithmetically not divisible by number 4 at all. Okay, now let's go through each case here. I'm simply going to replace this value of n into this setup and see what's the expression. Okay, so I get here 1 to the n is arithmetically is number 1. This one will have 2 square. This one I will have 3 square. This one will have 4 square. If you calculate this one, is given as 30. 30 is a congruent to 0 mod 5 because 5 divides this one. Now we are good to go. We have proven this one. Let's check this one now. So I'm doing the same thing, replacing this one into here. So I get 1, it stays always 1, plus 2 to the 2a, plus 3 to the 2a, plus 4 to the 2a. Let's make some change in here. This one is giving us 1 plus, this one is giving us 4 to the a. This one is giving us 9 to the a. This one is giving us 16 to the a. Let's reduce this one to mod 5. This one is clearly, I get 1 here. I get minus 1 to the a because 4 equals 5 minus number 1. Okay, I will be left with minus 1 to the a plus this one. 9 is clearly is a negative 1 to the a because we get one number less than 10. So I get here minus 1 to the a. 16 is clearly is 15 plus number 1, which is 1 to the a, which is number 1. But be careful, since we have a is a odd, this one turns into minus 1, this one turns into minus 1. Okay, so we get here 1 minus 1 minus 1 plus number 1. So this one cancelled out with this one cancelled out with this one. Now I will be left with is a congruent to 0 mod 5. Also this one is verified. We are good to go. Let's check the last one. I'm simply going to use the same argument that I have here. So I'm going to do it right away here. 1 plus 2 to the n. Let's simplify this one. We'll have 3 to the n. This one is clearly giving us minus 1 to the n because we know 4 equals 5 minus number 1. when you divide this one by 5, you get 0. I will be left with minus 1 to the n. As we said, n is an odd. So I'm reducing this one to mod 5, okay? So this one I will be left with 1 plus 2 to the n plus 3 to the n minus 1, okay? Now I get this one 0. I will be left with this one. So I get n is a congruent to 2 to the n plus 3 to the n mod 5, okay? Let's continue with this one. I get 2 to the n plus 3 to the n is the same as 5 minus 2, okay? I will be left with minus 2 to the n, okay? Because I get here 3, because I get 3 equals 5 minus 2, okay? So raising the exponent to the n and reducing this one to mod 5, I get 0 here. I will be left with minus 2 to the n. So that's what I did here, okay? I'm going to take minus 1 to the n out of this one. I get minus 1 to the n is multiplied by 2 to the n. So when is a congruent, I'm going to take 2 to the n as a common factor. I get 2 to the n factor 1 minus 1 to the n is multiplied 2 to the n. We know since n is odd, this one is towards minus 1. So they will have 1 minus 1, which is 0. 0 is multiplied by 2 to the n, which is 0. I get this one is a congruent to 0 mod 5, okay? So I have proven this one as well. Since we get to this one here, I'm going to do this one in different way. Since we have n is odd, I'm going to factor out this one on the form of a product. So I get 2 to the n plus 3 to the n, which equals 2 plus 3 factor 2 to the n minus 1 minus 3 is multiplied by 2 to the n minus 2 plus 3 squared is multiplied by 2 to the n minus 3, and all the way down until you get 3 to the n minus 1, like this, okay? So all what we care about, we are not going to care about this one, we care about this one. This is 5, okay? So when it's telling us 5 divides 2 to the n plus 3 to the n, okay, which we have here, which means is a congruent to 0 mod 5, okay? For verification purposes, I'm going just to consider n is a multiple of 4. We will see at the end this one, it cannot be divisible by number 5, okay? Let's assume 4 divides n, this one according to the divisibility statement. So this one will have n equals 4 is multiplied by k, which means n is a multiple of 4, okay? I'm simply going to take this value of n and insert it back into here. So I get here 1 stays 1, 2 to the 4k plus 3 to the 4k plus 4 to the 4k, like this, okay? So I'm going to calculate this one, but I'm going to leave 2k as an exponent. So we'll have 1 plus 2 to the 2, which is 4, to the 2k. This one I will have the same thing. I will have 3 squared, I will have 9 to the 2k, plus I will have 16 to the 2k, like this. Why I'm doing this one? If you take a look here, the exponent, whatever the value of k is, the exponent is always even, okay? When we reduce this one to mod 5, we will see something here. Let's reduce this one to mod 5. I will have 1 plus this one becomes minus 1 to the 2k. So everybody knows why I'm doing this one, because why this one turns into this one, because you know 4 equals 5 minus number 1. This one also will have minus 1 to the 2k, except this one. This one, it's clearly is number 1, because we have 15 plus number 1. So we'll have number 1 here, okay? This is the reason why this one never ever divisible by number 5. Because you keeping the exponent always even here, make this minus number 1 towards number 1, not minus number 1. So which means when you add together, you will have always you have 0. Because you have number 1 here, you have number 1 here. Mix everything is turned congruent to 0 mod 5, okay? It's giving us 1 plus 1 plus 1 plus 1, which is a congruent to 4 mod 5. So when it's telling us 5 cannot divide this number, okay, which is this one. So I have ended this video. By the way, don't forget to hit the subscribe button and support our channel, and thank you for watching. We'll see you next video. Bye.